The magnetic field existing in a region is given by the vector B is equal to B naught 1 plus x by L k cap. You observe this magnetic field, the equation, as x changes, the magnetic field is changing. That means as you move along x-axis, you will experience different type of magnetic field. That means stronger and stronger magnetic field as you move along positive x-axis. As x increases, the magnitude of magnetic field will go on increasing. But remember, its direction is not along x-axis, it is along z-axis, k cap. So magnetic field is directed along k cap, but its magnitude will go on changing along x-axis. Next, a square loop of edge L, so here is a L, carrying current I is placed with its edges parallel to xy axis. Then magnitude of the net magnetic force experienced by the loop is kB not IL. So what is K? Okay, so we'll draw the diagram to represent all the loop, magnetic field and everything. Okay, so first of all, we will represent x, y and z axis. So this is x, say this is y and this is z. And here I will represent a loop which is along xy plane. So here the loop is placed and it's a square loop. All sides are equal. So it is placed like this. Yes. So I'll name it as O, A, B, C. Let it carry current like this. So when it carries current like this, it will experience a force and a torque also. But the type of force experienced by all the sides are not equal, because you see the formula for magnetic field, B is equal to B naught into 1 plus x by L into k cap. This is the magnetic field. And as you move along x-axis like this, as x value increases, B will also go on increasing, but its direction is along k cap. What do you mean by that? Magnetic field here, when you are at the origin, if you put x equals 0, then B is equal to B naught. At the origin, the magnetic field is directed like this and it is weak. As you move along x-axis, as you move forward, the magnetic field is directed along z-axis, but its value will be stronger. Here, much stronger. Here, much more stronger. So as you move along this direction, the magnetic field will be directed along z-axis, but its value will be very, very strong as you move along x-axis. So direction of magnetic field is along z, but its value will keep on increasing as you move along x-axis. So this is the type of magnetic field. So now if you observe the square loop, this part of the square loop, for example, this part and this part of the square loop, if you observe these two, that means OA and BC, they will experience equal and opposite force, because the force is equal. The reason is, even if the magnetic field is different, suppose you take this part of the wire here in OA, the magnetic field from here to here will change, and it will be some value of strength here, magnetic field like this. But here also, the same amount of magnetic field will be along that axis. So what amount of magnetic field is experienced here by the side OA, the same amount of magnetic field will be experienced by this part of the wire BC here. And what amount of magnetic field is present here, the same amount of magnetic field will be present here also. So even if the magnetic field in the region of BC is different at different points, the same difference can be seen here also. The what magnetic force OA will experience. And if you want to know what is the direction, we'll see the direction. I'll rub the unwanted things here. Yeah, yes. Yes. Okay. This is also not needed. Yes. I'll rub this. Okay. Now I'll explain. Now, what is the force experienced by OA on this? You have to stretch the 3 fingers of the left hand. Middle finger should represent this direction, middle finger, because it is the direction of current. And magnetic field is outward because it is along z axis. So magnetic field means 4 finger should come out. Then what is the direction of thumb? Thumb will show this direction. So this is the direction of force. So this is the direction of force experienced by OA. Now what about CB? For CB, the middle finger should be representing the direction of current, and it should be like this. Middle finger in the direction of current, and the left hand forefinger should be coming out of the paper or out of the screen. This is the magnetic field because it is along z-axis coming out of the paper. Then now the thumb represents like this. This is the direction of force or thumb. So the direction of force is like this. So you see the direction F on BC. F on BC and OA will cancel each other. Reason, they will be experiencing the same amount of magnetic field at every part. Whatever the magnetic field exists here, the same amount of magnetic field exists here. Whatever the magnetic field exists here, the same amount exists here also. Because they are lying at the same x distance from origin, so the magnetic field changes with the x-axis only. Okay, so the force experienced by OA and force experienced by BC are equal and opposite. They cancel. So F on OA is equal and opposite to F on BC. They cancel. They cancel out. Now our question is the magnitude of the net force experienced by the loop. That means what is the remaining force? Remaining force on AB, that is how much, and force on CO is how much. That's what you have to find it out. Of course, they are in opposite direction. You can apply Fleming's left-hand rule and you can find out what is the direction of force. This will experience a force like this, and this will experience a force like this. You'll have to subtract it however. But what the thing difference here is, this OC is in the origin, and AB is along x-axis at a distance L, because you know the length of each side is L, so x equal to L. So I'll rub unwanted things. There are so many lines here, so I can rub this, yes. Okay. Yes. I can retain only the necessary things here. Okay. Now, if I try to write the force, this force is in this direction and this force is in this direction. That is cancelling. But what about this? So this force is like this, and here it is like this. They won't cancel because in the region where this is present, the magnetic field is different from the region where this is present. Now, if you want me to write the force on different points, this conductor is lying at a distance L from the origin. So what is the magnetic field existing in the region of CO? So here magnetic field is B is equal to, or I can write the only magnitude. You have to just write the formula with the x is equal to L, that's all. Magnetic field in the region of OA here, in the region of AB, that is equal to, so if you have formula here, B is equal to B naught into 1 plus x by L into k cap. So VAB, that means the magnetic field in this region at a distance L, B naught into 1 plus x is L by L, and that implies here B in the region of AB is, this is L by L is 2B naught. What about the magnetic field in the region of AB? So here, CO, magnetic field in the region of CO is, that is put x equal to 0, B naught into 1 plus 0 by L, that is equal to B naught. So now write the force on CO and force on AB. Force on CO, force acting on any conductor placed in a magnetic field is F is equal to current carrying conductor I into L cross B. That is in magnitude wise, you can write it as ILB sine theta. And here sine theta is sine 90 because IL and B magnetic field is along Z axis, so it is sine 90. So F on AB, is I, length of the conductor is L, because side is L. B is B in the place of AB is 2B naught. What is the force on CO, which is on the starting, it's one side is at origin. F on CO is equal to I, same I, L is L. B is B naught on the place where CO is placed, B naught. So what is the net force? Net force is FAB minus FCO, because AB will experience more force since it is in a stronger region of magnetic field. Everything else will be the same. So FAB minus FCO, that is equal to ILB naught minus 2ILB naught. That is ILB naught. 2 minus 1, that's all. So ILB naught. So now their question is, the net force experienced is KILB naught. What is K? So if it is KILB naught, then K is 1. Yes, that's all. Thank you.